A patient arrives at the clinic presenting with a staggering gait, severe intention tremors in their hands, and a shrinking tunnel-like visual field. Their medical history shows a diet heavily reliant on apex predator fish like swordfish and tuna. Suspecting heavy metal toxicity, the attending physician orders a standard 24-hour urine screen. The laboratory report comes back perfectly normal, measuring less than 2.0 micrograms per liter. The physician clears the patient. But while the lab report stays clean, high concentrations of methylmercury continue to dismantle the cerebellum and visual cortex, entirely undetected by the requested test. The error lies in the biological transport system. Organic methylmercury acquired from seafood is excreted almost exclusively through the liver into the bile, and finally out through the gastrointestinal tract. It does not pass significantly into the renal system. Relying on standard urine testing for this specific toxin guarantees the patient will suffer permanent neurotoxicity. To catch it, clinicians have to completely rethink how this element infiltrates the human architecture. Element 80 on the periodic table is a pure xenobiotic transition metal. It is a highly volatile liquid at room temperature, and it possesses absolutely zero recognized biological function in human physiology. Billions of years ago, early single-celled life evolved in environments completely surrounded by volcanic mercury degassing. To survive, they developed specific genetic blueprints, primitive detoxification enzymes called Mer-A and Mer-B. These systems could break the mercury bonds and vent the toxin outward as a harmless gas. As life evolved into more complex multicellular organisms, that genetic sequence was left behind. Higher eukaryotes completely abandoned the Mer-A and Mer-B enzyme systems. Modern human cellular architecture operates without any biological defense mechanism or metabolic pathway to process this metal. We are entirely defenseless against cumulative exposure. That exposure primarily originates in the ocean. Aquatic anaerobic bacteria absorb inorganic mercury and convert it into a highly toxic organic form called methylmercury. Through biomagnification, this compound concentrates at every step up the food chain, eventually accumulating in massive quantities within the muscle tissues of long-lived apex predators. When we consume those fish, the methylmercury enters our bloodstream and immediately seeks a binding partner. It locks onto the sulfhydryl groups of an amino acid called free L-cysteine. When these two molecules combine, their three-dimensional shape transforms. The methylmercury-cysteine complex morphs into a nearly perfect structural duplicate of an entirely different essential nutrient, the amino acid L-methionine. Because it looks exactly like vital food, the brain's heavily guarded gateway is fooled. Carrier proteins called the large neutral amino acid transporter 1, or LAT1, actively grab the imposter and pull it straight across the endothelial tight junctions of the blood-brain barrier. The infiltration continues in the gut. The liver secretes methylmercury into the bile to clear it, but as it travels through the small intestine, over 80% of it is actively reabsorbed in the distal ileum via enterohepatic recycling loops, trapping the heavy metal inside. Human architecture becomes its own worst enemy, using its most essential transport energy to actively ferry a toxic metal across its most protected biological boundaries. Once inside the cells, the breakdown begins with the antioxidant defense network, specifically critical enzymes called thioredoxin reductases, which rely on a core of selenium to function. This comparative scale shows mercury's chemical affinities. It binds to selenium with an attraction 1 million times stronger than it binds to sulfur. This irreversible lock permanently deactivates the cell's internal defenses, triggering massive oxidative stress and fatal lipid peroxidation. With the defenses down, the structural damage accelerates. Methylmercury binds directly to alpha and beta tubulin dimers. This instantly freezes mitotic spindles and collapses the physical microtubule scaffolding that gives the cell its shape. During fetal development, cortical neurons rely entirely on that tubulin scaffolding to physically migrate across the brain. When mercury collapses those tracks, the neurons fail to reach their destinations, leading to devastating, irreversible neurodevelopmental deficits. The final blow occurs at the synapse. Mercury selectively accumulates inside astrocytes, where it deactivates the GLT1 transporters responsible for cleaning up neurotransmitters. Glutamate builds up in the synaptic gap, continuously hammering the next neuron and flooding it with calcium. The cascading failure, from selenoenzyme deactivation to microtubule disassembly, culminates in the synapse. The resulting massive calcium surge causes the mitochondria to uncouple, and the neuron literally excites itself to death. While the organic dietary pathway relies on molecular disguise, historical exposure followed a very different route. During the Industrial Revolution, hat makers constantly inhaled elemental mercury vapor, which was used to felt animal fur. When inhaled, this elemental mercury gas, known as HGO, is highly diffusible. It travels from the lungs into the blood and effortlessly crosses the blood-brain barrier without needing a transport carrier. But once the vapor is inside the brain tissue, a biological trap is sprung. An enzyme called catalase oxidizes the elemental gas, converting it into an inorganic divalent mercuric ion. That rapid chemical shift strips the mercury of its fat-soluble properties. It completely loses the physical characteristics needed to slip back out through cellular membranes. The inhaled gas sails through the body's defenses with ease, only to immediately burn its own exit routes. The inorganic mercury becomes permanently locked inside the cortex, slowly destroying the central nervous system over decades. Diagnosing this destruction brings us back to the initial clinical mismatch. If a physician suspects organic methylmercury exposure from seafood, the exact biological pathway dictates the test. They must order a whole blood total mercury screen, not a urine test. But drawing that blood introduces an immediate pre-analytical hazard. The rubber stoppers on standard phlebotomy tubes contain compounds that leach environmental mercury into the sample. Accurate testing requires a specialized royal blue trace element tube. Once collected, laboratories utilize the absolute gold standard for trace element analysis, the inductively coupled plasma mass spectrometer. This machine vaporizes the sample inside an argon plasma torch at roughly 8,000 Kelvin, matching the temperature of the sun's surface. Despite surviving the heat of a star, mercury still manages to sabotage the reading. It is highly volatile and incredibly sticky. The atoms adhere directly to the mass spectrometer's plastic introduction tubing and nebulizer walls, causing a memory effect that creates falsely elevated readings for the next patient sample. To defeat this anomaly, laboratory technicians must add a specialized chloroauric acid wash buffer to the machine. They literally use liquid gold to chemically complex the stuck mercury and flush it completely out of the system. Confirming a diagnosis of mercury toxicity is an exercise in overcoming technical deception, first at the biological level of the blood-brain barrier, and then at the mechanical level inside the mass spectrometer. If the laboratory confirms that whole blood mercury levels have hit 50.0 micrograms per liter, the hospital triggers an immediate clinical panic protocol. The primary medical response is to administer chelation therapy, utilizing drugs like succumer or dimercaprol. These molecules possess vicinal sulfhydryl groups that act as chemical claws. They serve as highly attractive bait, outcompeting the body's own tissues to pry the mercury away from cellular binding sites. They form a water-soluble complex that the kidneys can safely excrete. However, the clinical utility of this treatment is time-dependent. If the mercury isn't removed before the structural collapse of tubulin causes visible atrophy in the cerebellum, the neurological deficits become permanent. Chelation can extract the metal from the brain, but it cannot rebuild dead tissue. Once the cerebellar architecture has been lost, even a total clearance of the body burden will not restore the patient's gait or vision. Protecting the human architecture requires strict diagnostic stewardship. Matrix matching is non-negotiable. Urine tests are exclusively for monitoring industrial vapor exposure, while whole blood is mandatory for tracking dietary apex fish accumulation. Ordering heavy metal panels for generalized cognitive decline without a clear history of exposure is clinical waste. It drives false positives, triggers unnecessary chelation protocols, and ignores the precise toxikinetics of the metal. Billions of years ago, biology possessed the bacterial enzymes needed to dismantle this threat. By abandoning that genetic blueprint, higher eukaryotes left themselves exposed to an element uniquely suited to weaponize our own amino acid transport systems. Within the human architecture, the most dangerous threats are rarely the ones that try to break down the door. The most significant damage occurs when a toxin flawlessly mimics the exact building blocks we rely on to survive.